Today, I want to cover the fourth video for the best time to buy and sell stock series. This question looks like an extension of the third problem. We can make at most k non-overlapping transactions this time. The constraints are the following. K is at most 100, and both the length of the prices and the prices themselves are within 1000. There are two solutions I want to cover here. One is the dynamic programming solution, or the DP solution, which is more intuitive and requires a recursive function plus memorization. The other one is a direct extension of the solution we derived in the third video, for LeetCode 123. If you haven't seen that video, it is strongly recommended to watch it first. In the so-called top-down dynamic programming solution, you first need to come up with a reasonably transition function with a reasonable status. There are two key points here. A reasonable transition function means it has an optimal substructure, as there is no loop in the later span-out recursive structure. Reasonable status means the status can uniquely represent the state of each recursive status. A way to imagine this is to make sure that from the recursive function, you can build a directed tree with no back edges instead of a general graph. At the end, we need to make sure the time complexity is reasonable and falls under the given constraints. Now let's break it down. So we're covering dynamic programming solution. As we said, there are two key parts here. One is the transitions, and the other one is the status. Let's start with the transitions first. We need to know at each state what kind of transitions we'll have. First, we need to decide whether we are holding stock or not. So we might holding stock, or we might not be holding stock. If we're holding stock, there are two actions we can take. One is to sell it or do nothing. Similar to not holding stock status, we can either buy it or don't do anything. We will know that we actually have 4 different options in the transition. In fact, it's only 2 because we will know whether we hold or sell or not. So it's 4 or 2. But anyways, this is like O1 complexity for transitions. Now, how about the status? So first, we will need to know where we are. So we will have the number of days. This is ON. And we also need to know whether we are holding stock or not. So this is a Boolean, hold or not. This is 2 or O1. And in the end, we also need to know how many transactions have been done. This is K. This is OK. This is around 100. And here is around 1000. Overall, the complexity is within 1,000,000, which is totally doable with Python in a second. Now, let's write down the pseudocode for the dynamic programming. So first, we'll need to have some corner case checks. So for example, you are at the end of the whole array, or you already use up all the possible transactions up to K, then you can return earlier. And secondly, you will have some memorization. For example, if you have calculated the result for this status before, then you can just return it right away. And now, after that, we'll have a block of transition, which basically is covered on the right-hand side. At the end, we would like to update the memorization. And then we'll return the max profit we can get. This is the high level of what we're going to do in dynamic programming. We'll provide more details in the code implementation. This is the note from the third best time to buy and sell stock question. In that derived solution, we utilize 2 preprocess array, make sell prices, and the mixed profit with sell prices to speed up the calculation of the maximum profit we can get from 2 transactions. Now we would like to generalize this solution from number of 2 transactions to up to k transactions. And let's see how we did it last time. Make sell prices array is used to maintain the 0 transaction plus the highest sell price. And this max profit with sell prices array is used to maintain the transaction of 1 plus the sell price. Now, if we want to do it for up to k times, we basically need to redo this process k times, and following the same procedure. And at the end of it, we'll need to actually calculate max profit from left to right within on time. Since each of the calculation takes O(n) time, and we will do it first k time plus the last time, so the complexity is basically n times k plus 1. You can see this actually has lower constant compared to the dynamic program solution, so this solution is expected to run faster. And again, we'll cover more details in the code implementation. And now let's jump right into it. Let's start with the dynamic program solution. In this dynamic program solution, I would like to make some given information available as instance variables before we start calling the recursive function. Specifically, I will have self.prices equals to prices, self.k equals to k, and self.length equals to length of prices. After that, I would like to make a variable record to keep the status. Inner side, I will have -1 for underscore in range n. After it, I will have two possible status, so it's either holding start or not. In the outer loop, I will have the number of transactions, which is k. After that, we can finally make a code to the function called dp, and then I will fill in the value here later. Now, in terms of the function, dynamic programming, I will take a few variables in. The first one is called position, it's an integer. I will also have the status. Status is also an integer. It will be either 0, means that we are not holding anything, or 1, we are holding a stock. And after that, we also have to keep the number of transactions as an integer. At the end, we would like to return the max profit as an integer. Okay. Let's think about can fill in the contents here. We'll need to first check some corner cases. So if the position is already at the end of the array, of course, we cannot get any more profit, which will return 0. It's the same thing if we already have k transactions, k, which also returns 0 at this point. Otherwise, I'll check if the current status has been visited before. So based on our current definition, we'll first check the number of transactions, and then the status, and then the position. So if this guy is not equal to -1, we know that this value has been filled in before, so we should just return this guy directly. Okay, if none of these three conditions happen, it means that it's the first time for us visiting this status, then we should just first default the max profit to dp position plus 1, and status remains the same, and the number of transactions remains the same. So this is basically telling us that we're not doing anything. We decide to move on, no matter we're holding a stock or not holding a stock, we don't do anything. We just stay the same. And this is the base case. Now, if we are holding stock, so if status equals to 1, then we can decide to sell it now. We can decide the max profit by maximizing the max profit at dp position plus 1 status. Because previous is 1, now once I sell it, we're not holding stock anymore, so it becomes 0. The number of transactions, however, will be plus 1 because we sell the stock, and then we'll also get the price of selling that stock. So this is prices of position. Otherwise, if we're not holding stock, then we can decide to actually buy it. So it will be position plus 1. 1 means now we are holding stock. Number of transactions, however, will remain the same because we haven't finished it, right? We just start buying a stock. We will increase the number of transactions after we sell it. But at this moment, we will need to pay the price to buy the stock. At the end, we'll need to update this guy with the max profit and also return the max profit. Now it becomes clear that before we call the dynamic function, we will need to fill in all 3 zeros as the input variables. And this should give us the expected results we want. And let's test it out. All right, so this should be self.n. Let's run it again. It seems that we're missing the self notation in many different places. Now let's add them. Here, 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 this guy, and over here, and over here. Now let's run again. Cool. Now we passed all the cases. Now let's do submission. Also, you can see the speed is not so good. It beats around 40% of users, and the runtime is around 200 ms. Now let's move on to the extension of the solution we found in the third problem. And let me comment out this one. I'll reuse this function signature from here. In order to save some time, I'm going to copy paste the solution from the third problem, where you can have at most 2 transactions. You're going to see how I make extension to it, and now it can take up to k transactions. So here is the code from the third problem. And I'm going to first rename this variable to be next profit plus sell prices at each transaction. This guy is not a one-dimensional array anymore, but rather it needs to have additional dimension for the k transactions. Now, with this guy, I can use it to update the following variable names. The first for loop, I'm going to prepare the max profit from case transaction, which is 0, means that there hasn't been any transaction, but I know the sell price for each location. Of course, this will be also at 0 transaction. After this, I'm going to this part. In the following for loops, I will need to know the maximum profit from each transaction plus the sell price before the next transaction finishes. So I don't need to use this array anymore because I already have the k-dimension array here. So I'm going to kill this guy. And I'm going to introduce another for loop for k transaction. So for JDX in range k minus 1, if I have 2 transactions, we only need to do it once here. If I have k transactions, we'll need to do k minus 1 times here. So I will need to tap everything inside here. Now, I'm going to maintain the max profit at k transaction in a different variable. Of course, I'm going to update this guy and this guy to that value. Also this guy. So how do we want to update this max profit at case transaction variable? Its value is updated with itself and the max sell price from the previous transaction. So it will be JDX. JDX starts from 0, which is this array of values that we have prepared before. Once we have this max profit at case transaction value, then we'll use this to update the value at JDX plus 1 in preparation of the next transaction. This will be also JDX plus 1. At the end of the for loop, we need to update the max profit with the max profit and the max profit at case transaction. Now, at the end of this for loop, we know the max profit we can get with up to k minus 1 transaction. On top of that, we also know the max profit plus sell price at k minus 1 transaction. So in the final for loop, we're going to also update this variable here. This guy will be maximum of itself, as well as this max profit plus sell prices at k minus 1. Of course, we need to do this max profit equals to max profit and the max profit at case transaction. At the end, we'll return this max profit value. Now, you see how I make extension from the previous solution up to 2 transactions to now we can actually handle up to k transactions. Now, let's just click run and see how it goes. Right? Again, it passed both cases. Now let's do the submission. Now you can see the runtime gets accelerated a lot, right? So it's from previous like around 200 milliseconds, now it's only 90 milliseconds, and it beats around 90% of the users. That's the wrap up of this video, and I hope that you like it. Thank you for watching.